Okay, so can everyone see the first slide, the cover slide? Yes, okay, good. All righty. So first I'm going to do my old teaching thing is I'm going to tell you what I'm going to tell you, then I'm going to tell you, and then I'm going to tell you what I told you. Sam probably knows that from teaching. Anyway, so we're going to talk about the hardware. We're going to talk about how good is the hardware. Then, unfortunately, there's a short physics class, but the good news is that everyone who leaves today will leave with a degree in physics. I have them printed up, ready to go. And then what are we gonna do with all this hardware, whether it's good or not? So first, let's start with the hardware. So this is the observatory being built on top of a ridge at the Cerro Pachon Mountains in Chile in South America. And there's a little picture of Calypso. You could do an entire talk just on that. Calypso was a privately owned observatory in Arizona that got shipped down there. And Calypso is going to follow Vera Rubin in the sky. And whatever Vera Rubin takes a picture of, Calypso is going to collect data so they can do a reverse adaptive optics, because Vera Rubin is not an adaptive optics telescope, but they're going to try to back calculate the adaptive optics after the fact using Calypso. So that's an interesting little telescope next to Vera Rubin. So here's the telescope itself. The actual OTA, or the mechanics, were built in Spain by a company called Aura. That's the big picture on the right. On the upper left is the artist rendition of the optical design, which we're going to talk about. And on the bottom left is the giant 8.4-meter mirror, primary and tertiary, being ground out of the same blank underneath the football stadium at the University of Arizona at the Steward Laboratory. So here's the optics. It's a very interesting system. It's a folded system, meaning that the light, has a tortuous path before it makes it to the camera. And there's a bunch of people sitting on the blank before it got ground in the University of Arizona. And there they are loading the 52,000 pounds of low expansion O'Hara Japanese glass that they're going to melt and spin. It's a spin cast mirror. They melt the glass, they spin it. That gives it kind of a good rough shape so they don't have to grind so much. And there it is being ground. That's at the University of Arizona's football stadium in the basement, sort of. If you ever get a chance to go there and visit the Steward Laboratory, it's an amazing place. And there's the primary and tertiary being ground out of the same piece of glass. So this is the primary. I don't know if you can see my cursor. The secondary, the tertiary ground out of the same piece, and then 3 lenses before it gets to the camera, right? And the red thing is the camera, which is pretty much all of tonight's talk. And one thing I want you to notice that the L1 and L2, the first and second corrector lenses, are 1.55 meters and 1.10 meters. And the last lens, by the way, is the vacuum seal for the camera. And it has to be ground in such a way that when you pull it under vacuum and it deflects a bunch of millimeters or centimeters, that it's the right figure. So this is like another miracle that has to happen. And just as a reference, the largest claimed single lens in the world is 40 inches. L1 and L2 is bigger, a lot bigger, 1.5 times bigger than the Yerkes Observatory in Wisconsin. So these are really big lenses. And someone might ask, well, wait a minute, I thought that the Yerkes telescope had a problem. They couldn't go any bigger because it would sag. How come these lenses don't sag? And the answer is because they're so fast. They have so much curvature that they're way stiffer than the long focal length Yerkes refractor. So they got away with making much bigger lenses because they have so much curvature, they have inherent stiffness from their shape, which is just amazing. So these are now the 2 biggest lenses ever made, but they call this the largest refracting lenses, and these are correcting lenses. So I guess Yerkes can keep its title, but maybe not so much. So getting to the camera. So the camera was developed and built on Long Island. What do I mean by developed and built? I mean everything. Like, we did the sensor development and testing. We did all the electronics and software development and testing. We did the camera design and testing. We did all the engineering, all the fabrication, and the delivery. And I added delivery because it was no less of a feat than everything else. I mean, we had to deliver an extremely sensitive, expensive instrument first across the country, and then from California, where it gets assembled into the cryostat, to Chile. And that was a big engineering project, was building things to survive this, taking off in an airplane, landing, nothing, not a simple task. Nothing was a simple task. In fact, it's funny if you saw the interview on YouTube by Earth Sky, they said, well, what would you consider the most challenging part? I said, everything. every day was a nightmare. Every day was like, oh my God, how are we going to do this? We had to have a miracle happen every day to get through this project. So what about the sensor? So this is the sensor. This is the crux of the camera. It's a 16 megapixel sensor. It's square. It's 10 micron pixels, which may seem big, but don't forget, this is a 10,000 millimeter focal length telescope. It's a 10-meter focal length telescope. It's got low read noise for a CCD. It's not a CMOS. And there's all the other specs. A lot of specs for the sensor, and the specs for the sensor is a several hundred page book. So I don't want to list everything. I'm just listing kind of the important stuff. It's special in that all the electronics are behind it. It's not the only sensor ever built like this, but it's very rare for camera and sensor manufacturers to build the electronics behind it. Normally they're off to the side, which makes it much easier to build. So all the electronics are behind the actual detecting portion of the sensor. So how big is it? Well, people know full frame sensors, right? A full frame sensor is 24 by 36. It's left over from the film days. Ken could probably do a talk on that why they picked 36 by 24 for film, but that
Steve may have a connection problem. He's on.
a
So
full
we
frame
won't.
sensor
There he is.
camera.
Okay.
Oh, did I blank out?
For a sec.
Yeah, I'm on Starlink. Sorry. Oh, it says my internet connection is unstable. Let's hope that comes back. All right, I hope you can still hear me. So, if you have a full frame camera for astronomy, if you got an extra $5,000 to spend, it's a great thing to have. It's a really giant sensor. But we don't have just one. We have 9 on what we call a raft or a raft tower module, right? So there's 9 of these sensors. They're in groups of 3. Each 3 gets its own electronic board. So you can see behind it, those green things are fiberglass electronic boards with lots of electronics. So this is now a full frame sensor compared to our raft sensor. And this is what's interesting. A single raft tower module is probably better than any camera in any telescope on Earth today. And why have, one of these when you can have 21 of these? So we have 21 of what would be considered the best camera on Earth today for a telescope. So we have a giant sensor. This sensor is huge. There's 189 of these 16 megapixel CCDs. We have to keep the sensors at minus 100 degrees and the electronics at minus 40. And this was a big challenge for me. This is most of my effort in engineering on the project, besides running the meetings and stuff like that. I had to keep the thing at these 2 different temperatures, and they're very different temperatures, and that was a problem. And we'll talk about it. So here, by the way, here's now a full frame sensor, what would be like the holy grail for most amateur astronomers. And here's the LSST or Vera Rubin sensor. It's 2 feet by 2 feet. It's a coffee table, basically. And there it is. That's a full artist, not artist, that's a full, mock-up of the sensor. And that's the field of view, by the way. The field of view is gigantic. It's, it's 3.5 degrees by 3.5 degrees. It's 7 full moons by 7 full moons at 0.2 arc seconds per pixel. It's super high resolution. And this is sort of the claim to fame of the telescope. So they did test images. What they would do is they would take a pinhole projection of an existing photograph. So the photograph itself might have distortions, but that pinhole projection of it has none. I don't know if people know, but a pinhole camera has 0 distortion. There is no distortion in a pinhole camera. There's no Petzval, there's no spherical aberration. It may not be the sharpest image, but it's distortion-free, a pinhole camera. So what they do is they take a pinhole projection of an existing image, use the LSST camera to take a picture of that and look for additional distortions. And if there's none, you pass. And if there's not, you did something wrong. So they took a pinhole projection of all the people that worked on it, and the 3rd row down is Brookhaven National Laboratory. Not a whole lot of people, by the way. In the beginning, it was just 4 of us. We were volunteers. We would meet on Tuesdays and Thursdays for lunch for 2 years until we got funding. And when we were fully staffed, we were maybe like, like a dozen people. By the way, Jessica Lee in the audience is one of those people, but she didn't make it into this picture, which I'm very disappointed about. But I did. So there I am, and there's Paul O'Connor, the chief sensor scientist, Sven Herman, the chief electronics engineer, Justine Haupt, the chief optical engineer and tester, and then a whole bunch of support staff. Oh, Peter Takis, the metrologist. So wasn't a whole lot of people though that built the camera. It's not like a NASA project. It's a dozen people or so. And there's the camera, complete. This is the sensors installed into the cryostat, with the front lens being the vacuum seal, and the next two lenses are actually part of the camera. And it's about the size of a bus. It's the size of a school bus in size and weight. It's a gigantic camera. It's the biggest camera ever built on Earth, and probably will ever be. And my part of it. So my part was, I had to model the thermal properties of the camera and structural properties, thermal and structural properties. So I built a model. So these are computer models of all the parts and pieces of the camera. And I'm talking every single part, the connectors, the copper inside the connectors, the copper inside the flex cables, the amplifiers on the sensors, everything. And you run it through a computer model that takes, sometimes hours or days or weeks to run. And you come up with results of what the temperatures will be. And what's really interesting, I don't know if you can see at home or on the screen, see these little red dots? I had no idea this was going to come out. These are the amplifiers behind the silicon on the sensors. And I threw them in like almost like half-fast, saying, that'll never matter in this model. And there they are, the amplifiers being a little hotter than everything else. And by the way, the range here is 3 degrees Celsius. And that was sort of our spec. We had to keep the temperature minus 100 degrees plus or minus 1.5 degrees Celsius. And we kind of just made it. But I couldn't believe that the amplifiers showed up in the model. It was just amazing. And the problem was that we needed to have this minus 100 and the stuff almost touching it, the electronics at minus 40. The reason being that you can't get electronics that run at minus 100, and the sensors needed to be minus 100 for noise reasons. So we had to have things 60 degrees apart, but millimeters apart. And that's why we have these very thin flex circuits. These are deliberately to let the temperature change from minus 100 to minus 40. And we accomplished that, but not easily. It took, many years, to be honest, to do this.
Steve,
Yes.
just curious, you said you built the electronics on the back of the sensors and that this was difficult. Wouldn't it have been easier to manage the temperature if these things were further apart?
Oh, yeah, but then the galaxies and nebulas get lost between them. This is an image sensor.
No, the electronics behind. If the
And
electronics behind were not so closely attached.
Oh, no, but they needed to be, because this is the space we had to live with. There's
Oh,
only,
okay.
there's, like I said, there's probably a 1,000-page book of the specs we had to meet, and size and weight is one of them. So we had to stuff all this stuff into zero space, basically, which is true of every project I've ever worked on.
I didn't realize it was a space issue.
Yeah,
Okay,
it's
thank
also
you.
a space issue.
Yeah, thank you.
And you can't have these flex circuits too long either, or they lose signal. It's like a USB connection, but not really. So here's I built this test chamber out of scraps because they wouldn't give me any money to do it. So Justine had a leftover chamber, and the vacuum group over in the collider department had stuff, and I literally glommed stuff together. And this is one of the first engineering grade sensors. So there's science grade and engineering grade. An engineering grade sensor lets us test it, but may or may not end up into the camera in the end. So these are used for testing. So this is one of the 9 testing. First, we started with 1, eventually 9, and eventually a real raft, and this is going into the chamber, and there's, sort of this is the raft tower. This is a silicon base for all the sensors. And then we use a lot of copper because we got to get the heat out. The minus 100 degrees C all has to go someplace. So lots of copper, and lots of electronics and lots of wires. And then I have RTDs and thermocouples and heaters and all kinds of stuff. So there's me next to the sensor, the test chamber. And there's the late, great Phil Kashevsky, a former ASLI Custer AOS member. He was a genius. I wouldn't have been able to do any of this without him. He was an electronics genius, and also LabVIEW software, which runs all the programs that did all the tests I conducted inside the chamber. So I wouldn't have been able to do it without Phil. And there's Jessica holding the little IR window that we use to heat the sensor as if it was facing space or something else that's hotter than minus 100. So Jessica was also a part of this test chamber testing facility. And here's another funny thing. They wouldn't give me any money to build this chamber, but the second it was done, they had 1,000 tests they wanted me to do. And, and then it gets even funnier. Then when we were done with it, they wanted to throw it out, and I gave it to the Collider Accelerator department, and they've been using it for about the last 7 years, with a nonstop list of people waiting to use this cryogenic vacuum test chamber with an infrared glass window. So it's never stopped. This test chamber is still going, the one that they wouldn't give us money for. But that's classic at Brookhaven Lab. They refuse to give you something, and then when you finally build it, everybody wants it. So, but anyway, that's And it's okay. There. And there it is. There's a raft being installed at SLAC, the Stanford Linear Accelerator Center in Stanford, California. They were our boss, sort of. They were the ones paying us to build the sensor rafts. And there it is going into the full array. That's in another silicon grid. So this is a silicon grid. That's a silicon grid. And why silicon? Because it doesn't expand thermally. And by the way, all of this entire sensor, this coffee table sensor, the flatness, in other words, the distance from one height of one sensor to another had to be about a 20th of the thickness of a human hair. That was the spec, that you couldn't have the sensor being higher or lower than another sensor by a 20th of a human hair thickness because it would be out of focus at f1.2 and 10,000 millimeter focal length. So we had to be flat to be in focus everywhere. So there's now the lenses going in. This is now the camera. The camera is gigantic, by the way. I know these are people standing here, right? This is a really big camera. And there it is. There's the camera. And it's being installed with a crane, a special crane made for this to go into the telescope. And it faces the primary, mirror like an SCT Hyperstar or RASA telescope, very similar. And it's huge. And by the way, the camera also rotates. It's on a rotator because this is an alt-azimuth mount. So we have to rotate to prevent field rotation. It's not a full 360 rotation, but it rotates, during images. So it's an amazing device. And first light. So here we go. So this was recently. I got invited up to Brookhaven Lab to witness first light that was done through Zoom. And it's taking pictures now. This is an engineering run. So now we're up to how good is the hardware? Part 2 of the presentation. So how good is the hardware? Well, I compare it to other telescopes. So the LSST, or Vera Rubin, is on the left. It's an 8.4 meter mirror. It's, by the way, there's only 5 telescopes on Earth in this size class. And that's it. There's not a whole lot of big telescopes like this. Keck is another one. Keck has 2. Also, by the way, these mirrors were also ground at the Steward Laboratory in Arizona. And it has 9.96 meters, but the same class. And then I have the Sloan, which is a survey telescope. And I say that the Keck comparison is not a fair comparison because Keck is not a survey telescope. Keck is meant to look at one little tiny object at a time, not all the objects like a survey telescope. So I say it's not fair. And the field of view is tremendous on the LSST. It's 3.5 degrees by 3.5 degrees versus 0.03 by 0.13 on the Keck versus 1.12 by 1.34 on the Sloan. And there's a figure of merit called étendue. Étendue, it's a French word, and it multiplies the aperture by its field of view. This tells you how much data you can collect. This is a data collection figure. This is high resolution data, but how much of it, right? So these are numbers. Picture's always better. The LSST has the same resolution, that is the same arc seconds per pixel as Keck, except you would need 1,000 Kecks to get that same data in the same amount of time. This is like running 1,000 Keck telescopes all at once and different objects at the same time. This is the beauty of LSST. This is why it was built. Tony Tyson, the inventor of LSST, was frustrated as a scientist because anybody that wanted to get data on these large aperture class telescopes, of which there's only 5 in the world, would have to submit a proposal with a whole bunch of other scientists. And then that would go to a unbiased review committee. And they would decide if you would get 1 week on their telescope. And then if you were lucky, you did. And if you didn't, then you'd submit it again for the next year or the year next or the year next. And then you'd wait another year and submit another proposal. So people are getting 1 week at a time, 2 or 3 years apart. You can't do science this way. There's too much time between data collection. LSST solves that problem. It collects all the data. It does the entire sky in 3 nights. And it does this over and over and over again. So you can stack the data and you can see things changing because every 3 nights it goes back to that spot and you can see an asteroid that's moved or a supernova that's exploded or whatever. So anyway, so let's keep comparing, but rather than compare it to these giant telescopes, let's compare it to my telescopes. So when I first saw the release of the LSST image, my first reaction was, I don't know. I wasn't that impressed. I'm like, I don't know. I think I've seen amateurs do better. This is the Lagoon and Trifid, and this is my Lagoon and Trifid. And at first glance, I like mine better. You know, this is a 0.09 meter telescope, certainly not in the same class as an 8.4 meter telescope. But I was like, I don't know, their image is kind of crappy in my opinion. You know, as a photographer, I'm not really that pleased with their image, but you know, it's my tax money hard at work. But all right, so I said, all right, let me give them a chance here. And by the way, I do have the full res images. They're 51,480 by 84,060 pixels. I can't open it. And in any software I own. And then I asked the LSST people that they actually gave me a FITS file of the actual high res image, and they couldn't open it. And that's where we are today. They can't open their own data, not the people that I'm working with anyway. So these are like thumbnails, basically, right? This is a thumbnail of the original image. So keep that in mind as we progress through this. So I said, all right, let's just pick a spot. Let's pick the lagoon. So here's the Lagoon Nebula. And this is theirs and this is mine. And I'm still liking mine better. I think mine has more contrast and looks better. But let's give them a little help. So I give them a little help. And all right, the images, LSST is getting a little better. You know, we're on similar scales, by the way. This is like 2,300 by 3,400 pictures. Mine is 2,800 by 4,200. About actually a little less because it's not the full res image, 1.68 arc seconds per pixel versus 1.36. But all right, let's zoom in a little. And this is what matters in the end, and you'll see why. So we're going to zoom in a little. So there's their image and my image, and all right, theirs looks maybe a little better than mine now, right? It's, you know, it's sort of, I'm starting to see a few more details than my image shows. Let's zoom in one more time, right? So now we're zoomed in more, and now their image is looking better, and let's give their image a little help with some better contrast. And now it's amazing. Now, just remember, we're looking at a thumbnail of the original image, and look at the detail. It's blowing. It's like as if like this is like the first image without the zooming. And this is the whole point of LSST. You cannot appreciate its images unless you have like a 40-foot by 40-foot monitor. I mean, it's because of the resolution that makes LSST what it is. And it's because it's so big on the sky is what makes it that you don't need more telescopes. You just need this telescope, because it's going to get all the stuff in the sky as good as any giant telescope on Earth, but all at once, all at the same time, because of the giant camera. I mean, this is what makes LSST special. So to me, this is amazing that a thumbnail of their full resolution images just blows away anything I've ever seen, you know, from an amateur or even other observatories. So this is the beauty of LSST. Okay, so now for the short physics class, because I can't tell you how we're going to use this hardware until you have some understanding. So the short physics class that you get your degree in. All right, so in the 70s, Vera Rubin and Kent Ford in Institute in Washington are looking at punch cards. So nobody knows what that means, but I know what punch cards are because I used to use them. But they're looking at punch cards from a spectroscopic telescope. And the beauty of a spectroscopic telescope is it will show you redshift and blue shift. And this is how they could tell in Andromeda what its velocity is across the galaxy, right? Because Andromeda is close enough that you can do this. And there's something going wrong. It looks like, according to the punch cards, that the outside of Andromeda is moving just as fast as the inside. And this is a problem because according to Kepler's and Newton's laws that we've been using for a couple of 100 years, the closer stuff's supposed to go faster and the farther stuff is supposed to go slower. But the punch cards of the spectroscopic data is saying, no, 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 they're all moving at like the same rate, disobeying the laws of basically, you know, gravitational orbital motion, right? So this is a problem. This is the beginning of dark matter. So, you know, if you look at our solar system locally, it behaves, right? Mercury goes fast. Pluto, whether it's a planet or not, goes slow. But not the galaxy. The galaxy, even our own galaxy, you know, the outer arms are moving as fast or faster than the inside stuff, right? So this is the reason they call it dark matter, is because it's not accountable through the mass of the number of stars that we can see, right? So it's really non-luminous matter would have been a better word, but dark matter is the name it got, and that stuck. So Vera Rubin said, in a spiral galaxy, the ratio of dark to light matter, or non-luminous to light matter, is about a factor of 10. That's probably a good number for the ratio of our ignorance to knowledge. We're out of kindergarten, but we're only in about 3rd grade in astronomy, right? This is an amazing quote, right? She's saying that we don't know what the heck's going on. We're not off by percents. We're off by factors of 10. We would need 10 times as many stars that we can't see, you know, to create this kind of motion. So what is dark matter? Well, if you don't know, you're in good company because nobody knows. These are all the accepted, peer-reviewed, non-crackpot theories of dark matter in a Venn diagram by Tim Tate. I just love this diagram. And, there's everything. There's axioms, there's particles, there's modified Newtonian dynamics, gravitrons, all kinds of, explanations for what dark matter can be, but they're all theories at this point. We have not visually observed dark matter yet. We only see its effects. So how I like to explain it when I'm teaching an astronomy class at Suffolk is imagine you're two very evolved fish and you've just built your first telescope at the bottom of the ocean. And the first thing you're going to look at is a flag on land, on Earth, on terra firma. And it's moving. And the one fish says to the other scientist fish, "What's making that flag move? I don't see anything." And the other fish says, "Well, we think it's air." "What's air?" "Well, we think it's a third phase of matter." And the first fish says, no, wait, there's only two phases, solid and liquid. What do you mean a third phase of matter?" No, we think there's a third phase called gas, and the gas moves and it disturbs the flag. This is the level we're at with dark matter. We're the fish. We don't know what this is. We have no concept of what's making these stars move the way they're moving, and we can't see it, we can't detect it, and it's not just visible light. We can't detect it in every frequency we've tried. It's just not there. So anyway, so that's dark matter. So now you know what dark matter is. Well, you don't know what it is because nobody does, but you know what it does. Then we got to talk about redshift, and I think most people here know redshift. It's when some waves are moving towards you, they get compressed. And when they're moving away from you, they expand. So when they're moving away, they get shifted towards the red or a longer wavelength. And when they're coming towards you, they get shifted towards the blue or a higher frequency or shorter wavelength. And we don't just use the color, we use spectral lines because they're very accurate. The fingerprint of elements like hydrogen, helium, lithium, whatever is, creating these absorption or emission lines is exact. If you believe that everything that happens on your desk on Earth happens everywhere in the universe, the fingerprint of an element should not change. And we look at the shift of the spectral lines to tell us how fast something is moving towards us or away from us. So that is redshift. So there's your redshift degree. And now Edwin Hubble, he uses a combination of things. He uses Cepheid variable stars to get distance and redshift to get velocity, and creates a thing called Hubble's law, which is, pretty incredible. So we all know what parallax is, right? You hold your finger out and you close one eye and you close another eye and it seems to shift because the angle changes from your viewpoint, whether it's the right eye or your left eye, or in this case, the Earth on one side of the sun and the Earth on the other. And simple trigonometry says, if you can figure out that angle, if you can measure that angle change, you can calculate the length of a leg of the right triangle. So that's for stuff that's kind of close in our own galaxy. And what's good about that is we can first verify the Cepheid variable thing in our own galaxy, right? So we can do parallax nowadays up to about our own galaxy, because of measurements of angles being accurate. Then we use Cepheids outside our galaxy, and a Cepheid variable is a star that its frequency of varying is proportional to its intrinsic or true brightness. So if you know something's true brightness, if you know its apparent brightness, you know its distance, because that's an inverse square law, right? That the apparent brightness of a star drops, proportional to the inverse of the square of the distance. Just like with sound too, if you get twice as far from a sound, it seems 1/4 as, loud to you. And then when you want stuff really far out, you got to use supernovae and quasars and stuff like that. So these are sort of like the three steps, main steps of the distance ladder. You got parallax, Cepheids, and supernovae. So Edwin Hubble, looking at Cepheids in other galaxies, came up with a line, which it seemed to be a straight line, more or less, of distance from Earth versus velocity using redshift data. So it's Cepheid variable for distance, redshift for velocity, and it seems to be a constant. He had the constant wrong, but it wasn't wrong. There's nothing wrong in science. You just keep, redeveloping and reevaluating. But, he came up with that constant. And what's really important is, if velocity is h times d, using your basic, 9th grade algebra equation of a line, then d is v over h. And what this does is it says that once we know what the Hubble constant is, I only have to measure redshift to get distance. So it gets rid of a whole lot of work needed now to get distance to things. Now we can get distance to things very accurately by just measuring the redshift, which is their velocity. So this is huge in astronomy. This is a big breakthrough. This means, give me a spectroscope, calculate the shift. I know how far it is using Hubble's constant. Okay, Now in 2011, so we're fast forwarding from 1930 to 2011, Perlmutter, Schmidt, and Rees get the Nobel Prize for not only seeing that the universe is expanding like Hubble said, but it's accelerating. That it's very small differences in the data, but if you get enough data, you can beat down the error bar. They got enough data on supernovae. They were all in competition with each other, by the way, and that's a separate talk in and of itself, but they all three got the, they all kept their data secret back then in the late 90s and early 2000s. But anyway, they all got the Nobel Prize, and they're showing that the universe is not only expanding, but it's accelerating. So this starts another weird thing called dark energy. Because as I teach my physics students in Physics 101 or engineering dynamics, you can't have something go faster throwing a baseball than after it left your hand. It violates the conservation of energy rule. 1/2 mv squared initial has to equal 1/2 mv squared final. If you don't add additional energy, there's no way you can gain speed. The fastest that ball is going to go is when it leaves his hand, at least in the horizontal direction. So the universe is not only expanding, it's accelerating, which means something is adding energy to the galaxies to have them accelerate. And this energy is not invisible matter. It's not the stars. It's not things that glow in space. It's invisible. It's non-luminous energy or dark energy. So if we put these two together, dark matter and dark energy, and sum up either in mass or in joules, in energy, and you can do that because E equals mc squared, they can be made equivalent. The universe that we knew before all this is only 4.9% of the total mass of the universe. There's something weird here, right? There's, everything we've ever learned. Like I remember in school, the teachers used to say, everything's made of atoms. No, only 4.9% of things are made of atoms. There's another 95% that's made out of we don't know. And then there's different models. Like there's a model that shows that maybe the universe is not as old as we thought, and it's going to contract. It's going to stop accelerating, stop expanding, and contract on itself. And it's going to end up in a big crunch, right? And things will be very hot. It'll be like as hot as it was at the Big Bang. And then there's a flat universe, which is kind of what Einstein thought, that the universe is just flat. Then there's a expanding universe like Edwin Hubble, and now we think it's an accelerating universe, that it's actually going to tear itself apart, and not just galaxies, like atoms themselves will tear themselves apart. Like nucleus and protons, and neutrons and protons, electrons, that the whole universe is just going to, end up freezing, being very cold. And this is interesting because I always think that artists know more about science than we do. And Robert Frost said, some say the world will end in fire and some say in ice. So these are the fire and these are the ice believers. So anyway, so that's dark energy. A little more, and then the physics lesson's over. In 1919, Sir Arthur Eddington wants to photograph the total solar eclipse because Einstein predicted that gravity can bend light, right? This was an Einstein prediction that a large enough mass will put a big enough dent in space-time that even light will get bent, right? So that if you're looking at a star, it might be really here, but its apparent location because of the bending makes it look like it's as if the same that happens with atmospheric refraction, that you see the sun rise before it actually rose, right? So wait a minute, you're going to say photons, which is light, by definition, they have zero mass. How can they be affected by gravity, right? This bothers people. Wait a minute, how can something that has no mass be affected by gravity? Well, let's think about Galileo, right? Galileo showed that the acceleration of an object due to gravity is independent of its mass, even if its mass is zero. Right? Even the smallest object down to zero has the same acceleration, but you can't drop a photon because a photon by definition is always moving the speed of light. So don't let your brain think of it this way. Let your brain think of it this way, right? It's not the mass, but the velocity and gravity that determines how much bending of light you get. So if something is going slower than the speed of light, it might not even make it around that large mass, let's say our sun. Like this could be a comet that crashes into the sun. And if you're going faster, maybe a faster comet or some other object, then you're going to bend more. And if you're light, you're going to bend less, but never zero, because the object is affected by acceleration. And by the way, gravity is not a force, it's an acceleration. Gravity can cause a force, but you need mass to do that. So try not to think of it like an object falling, think of it that you're bending the road that light is traveling on, right? Light is traveling on this road, which is space-time, and heavy objects distort space-time, and they distort the road that light is traveling on. So if you think of it this way, it won't hurt your brain as much. So that ends the physics class. So what are we going to do with all this hardware? Well, as I said, one of the things we're going to look for in Vera Rubin is strong lensing. We want to see what things are being bent. And I don't know if you can see in this picture here, but these stretched out crazy lines are actually normal shaped galaxies, but they're behind these giant galaxies like the Coma cluster and Abell cluster and everything else. So that their light is so distorted that they even get split and stretched apart. It's barely recognizable, right? So this is strong lensing, and Vera Rubin will be collecting data on that. But more importantly, the most important thing is Vera Rubin's going to be looking at weak lensing. Weak lensing is going to show us where dark matter is. So right now, it seems like dark matter is mostly on the outsides of galaxies. And the reason we know that is because, or we suspect that, is because the outer things are moving faster than the inner ones. If dark matter was evenly, uniformly distributed across the galaxy, it would rotate like our solar system, and we wouldn't see this effect, right? So it's got to be that there's more dark matter on the outside than the inside. Otherwise, we go back to Newton's and Kepler's laws. But we don't know about the between the galaxies, right? What's happening between galaxies? We've never looked at that, but Vera Rubin will. So Vera Rubin's going to look at all of space, and we're going to try to map distortions of galaxies, and then we can find where dark matter is. So I don't know if in my lifetime we're going to know what dark matter is, but I'm hoping we're going to know where it is, right? Because before you can determine what something is, it would be good to know where it is, because we don't know. We don't know where the dark matter is. So now the question someone's going to ask, either now or at the end, is how do you know if a galaxy is distorted? How do you know it wasn't that shape to start with? And this is where statistics comes in. If we look at, let's say, 10 million galaxies that are close to us, close enough that we don't think dark matter has affected them, then we know for those 10 million galaxies what the normal shape of a galaxy is. And then if we look further out in space and see a change in that normal shape, then we say, oh, why aren't they the same as the first 10 million galaxies? And unless you have 10 million galaxies, you can't make this claim of what a normal galaxy should be. So if you look at enough galaxies, you can determine a normal shape and then maybe see through the progression of distance that shape change, and that would be an indication of dark matter. So that's how we're going to do it. We're going to do it with beating it to death with lots of data of lots of galaxies over lots of distances. So, okay, so we've covered 2.5 out of the 5 science goals for LSST. We've talked about dark matter. We've talked about dark energy. We talked a little bit about supernovae. In the cosmological sense, we talked about redshift of supernovae in Perlmutter, Schmidt, and Rees. But supernovae also fall under the astronomy category. And by the way, for people that don't know, and I know most do, but some don't in this group, the difference between cosmology and astronomy is like the difference of me looking at New York City from above and counting how many buildings and what their spacing is and maybe what the height differences are versus me looking at, well, what's that building made out of? Is it bricks? Is it cement? Is it wood? Right? So that's astronomy, and the big picture is cosmology, right? So supernovae by themselves have astronomical importance in terms of, well, when did it explode and what kind of light curve did it have? That's astronomy. That's not cosmology anymore. And then, of course, astronomy is mapping our own Milky Way galaxy in near-Earth objects. So supernovae. Vera Rubin will detect them, but it won't stick around to study them. It can't, because it takes two 15-second images and moves over and takes another two 15-second images and moves over. And it does this all night until the sun comes up. And it gets as many pictures of it as it can, and it repeats this over and over. So the only thing it can do is alert some other telescope to go look at a supernova after it discovers it. So the longest time you'll have between a supernova discovery will be 3 days. And if you're sitting on a computer at home tied into the Vera Rubin data, which will become public data, you can be the one that discovers that supernova because you'll look through the data and say, oh, look, I found one. And comets and asteroids and everything else. So Vera Rubin will be a supernovae detector, but not a observer. It'll move on, except for redshift and stuff. Mapping, it's going to detect 10 billion stars. That should, be impressive. With sufficient signal to noise and enough accurate light curves and geometric parallax, and proper motion to make a better map of the Milky Way, because it's not that easy. One of the things I used to tell my students is, imagine you're sitting in your living room and I ask you to draw me a picture of the roof of your house, but you're not allowed to go outside. You're inside the galaxy. It's hard to map something that you're on the inside of, but we're going to do a better job. And by the way, not to put down Gaia and Hipparchus and all these other great satellites that did a great job, mapping the galaxy. We're just going to, refine the data just like we refined the Hubble constant. Near-Earth objects. I don't know, people might not know this, but in 1998, it's a mandate of Congress that 90% of all near-Earth objects bigger than a kilometer in diameter have to be discovered by 2008. I don't know how you do that, because how would you know you didn't discover something? But it's Congress, so it's not that surprising. And in 2005, they decided to make it 140 meters because of, I think that might have been because of Chelyabinsk and the damage it did, which was only, I think that one was only like 3 meters or something, Chelyabinsk. But these are things that could cause harm to Earth. And you might say, what right does Congress have to tell an observatory what to do? But being that they paid for it, maybe they do have a right. Anyway, so Rubin's going to do this really good. And I always like that. Oh, look, a shooting star, make a wish. In the first 10-hour engineering run of Vera Rubin, it discovered 2,000 asteroids. 2,000 asteroids in 10 hours. So I hope that's impressive, because that's just amazing. And they were only looking in one part of the sky, and they only got asteroids in the asteroid belt, because that's where they were kind of facing. But that's just amazing that in a 10-hour engineering run, not the 10-year run, we're talking of running for 12 hours a night for 10 years, but in a 10-hour run, they got 2,000 new asteroids. So this is another thing Vera Rubin would do. And by the way, the final reason we got funding and we're able to stop working as volunteers on this is because of the addition of this telescope's capability, because everyone realized that the scope can do this in addition to doing dark matter, dark energy, supernovae, and mapping. And that got added on to a capability of the scope, and it pushed Vera Rubin up to the #1 project of the National Science Foundation and Department of Energy. And we got funding. And by the way, the reason you see red, green, blue here is because they're switching filters as they're taking these pictures. And the red, green, blue is the asteroid moving. It didn't stay, the filters you're on a different filter and the asteroid's in a different spot, so it doesn't stack the same. So anything that you see red, green, blue is an automatic detection of something that's moving versus something that's relatively stationary, even though technically everything's moving. So that's the near-Earth asteroid stuff. So the bottom line is, if you want something done, give it to a busy telescope. Ian.